cap A likewise. KYA capital I star minus Y times A. Now, I'm going to take this V over here. I'm going to take this M over L over here. I'm going to subtract these equations, divide by Y star minus Y, and I'm going to have D mx minus Y over mx minus Y. That's on that hand side. Over here, I'm going to have some stuff that I'll put there. But it looks like what I'm going to have is a dz times an A. What am I going to do with that A? Oh, I'm not going to do anything with that A. I'll just write the dz here for the time being. I've got a ky sitting here, kya. And I think what I'll do is factor out a v. So v over cap A. There's a group. And in here, what I'm going to have is m, took the v out, v over L, m v over L minus 1. Now I integrate this equation from the bottom to the top, and I have one of many equivalent dilute solute models. So I have one of many equivalent dilute solute models. And it is this. It is m x in minus y out. That's at z equal to h over mx out minus y in with a log equals m v over L minus 1. This thing has a name. It's called, Z is the height of the column, it's called HOY. So we've introduced something called HOY that includes a lot of ignorance on our part. We need to find HOY. There's a number of moves we've got to make to talk about doing that. But before we do that, we notice that, well, let's write down what HOY is. HOY has units of length. So the dimensions of HOY are L. HOY is KYA, a mass transfer coefficient, divided by V over A. Now what this basically is a ratio of 2 times. It's a reciprocal, well, this is more or less a measure of how fast mass transfer is taking place. This is more or less a measure of how much time you've got in the column. It might even be better if I would have put the H in there and say that, but nonetheless. So whenever you've got a long time in the column and a high rate of mass transfer, you should expect a small column height. Whenever you've got a slow rate of mass transfer and you've got not much time in the column, you should expect not much separation. So this thing has an interpretation. The O stands for overall. And overall means overall in the sense of U and heat transfer. And the Y stands for the fact that you've done this on the Y side. So it's called HOY. And it's equal to what it says there. Now, we have an equation here. It goes along with a balance. It goes along with a material balance. So it goes along with something that goes Lx in plus Vy in equals equals LX out plus VY out. And if you know the mass transfer characteristics of your column, and we'll have to talk about that, you're prepared to say something. So let's see what we can say. Maybe the boss says, I've got a, maybe I'm going to input X in L. Maybe I'm going to input Y in and V. Maybe I'm going to require a certain X out. And maybe what I want to do is find the height of the column to get this. So find the height of the column, find H to get that. So we will look at our equations over there. And if we, well, we're going to need M. So somehow I've got to go find M. That tells me about the equilibrium. I've got the V and the L. That's looking good. I'm going to try and calculate H out of that formula. If I'm given X in L, Y in and V, and I require an X out, I can go to this equation right here and get the Y out. So I go to that equation, and the first thing I do is get Y out. Now, once I get Y out, I notice that I've got everything in here but H. So I go and make this calculation, and I get a value of H, and I'm now ready to tell the boss that a certain number of height, like maybe 10 feet, with the packing that he likes to use, will do the job. Of course, I have to know, in addition to M, I have to know the mass transfer characteristics of my packing, so I got to know something about HOY. That requires me to know something about mass transfer coefficients, Kx and Ky, so I have to have that information sitting around, and also embedded in HOY are flow rates and the cross-sectional area of the column and so on. So, given all that I've gotten everything together, I then go calculate that H, and of course I can draw a picture of this calculation, and the picture goes something like this. Boss gives me a certain X in. He says, go make that X out. He says the equilibrium is Y equals MX. He says the YN is there. So you have that point. That's a fixed point. This represents the bottom of the column right now. That point I'm not going to move. That's the bottom of the column. I don't happen to know Y out until I make the calculation, so I go draw a line of slope L over V. That gives me the point X in Y out, and that is now the point at the top of the column. For every X in the column, that's the value of, this is the point whose coordinates are X and Y. This is the point whose coordinates are X and Y star. That distance right there is Y star minus Y. And so that distance right there is the available driving force for mass transfer in this column. And that driving force for mass transfer is going to integrate into that formula and give me a formula for the height of the column I need. So that picture is that equation.
Professor, you said that the slope for X to X in right here is
The slope of this is L over V.
L over V.
You can, well, yeah. Why is it L over V? Because if I make a balance around the top of the column down through wherever I'm working, the top of the column down through wherever I'm working, I write something like this. I write Vy is an in, Lx is an out, Vy in, Vy out out minus Lx in is an in. I divide this by L, a V, and I get Y equals L over Vx plus Y out minus L over Vx in. So, given these numbers here, this is a line of slope L over V. It clearly passes through the point Y equals Y out when X equals X in. Y equals Y out when X equals X in, but the total balance over there says it also passes through that point. So we have our usual construction making all the material. So all the material balances in the column are along here somewhere. Every one of them's in use. In every differential volume, I've got a driving force for mass transfer. If my driving force is big, my column's short. If my driving force is small, my column's high. So let's see what happens when we change. So the boss says, look, you told me this column was 10 feet high. In my garage, I've got one of these 3-story garages. I have 30 feet in there. I'll just put this column in my garage. We'll make it much higher. Can we cut back on the V? You say, well, I'll check that out. So you say, okay, let me repeat this calculation for a reduced V. Repeat at a lower V. Okay, now I'm not changing any of I'm not changing the X out he wants. I'm not changing the X in I'm given. I'm not changing the Y in I'm given. But this line has a different slope. And I'm now going to get a new point, Y out, which I get by drawing the new slope L over B, or going to the column at the bottom of that board over there and making a calculation. What has happened to me? What has happened to me is that if this is X in the column somewhere, this is now X and Y. The driving force at that point is now this distance is less. I've got less driving force throughout the column. With less driving force throughout the column, I expect to get a higher column. So you come and tell the boss, well, you know, we've made this 20 feet, and now the height of the column, well, we reduced V. The height of the column is now 20 feet. Somebody says, oh, go reduce it more. So you reduce it more. As you reduce V more, you will find that the Y out is moving up. Now that is not a surprise. The Y out's moving up, you see you're losing driving force up here, so the column's getting much higher. So there will come a time when you've reduced the V to there. You've lost the driving force entirely at that end of the column. The column's now infinitely high, and you cannot even come close to making the separation even with an infinite column. So that is called the minimum, the least V for that separation. So when you're specified an X in, an L, a Y, so if you're specified an X in, an L, a Y in, and an X out, you can go calculate a minimum V. That would give you an infinite column, but so you can reduce the V, you can increase the V up from there, reduce the size of the column, and come to some conclusion about how this thing ought to work. So that's step one. We have a model. Let's see how we're doing. What in the world? Oh!
You didn't switch the time?
I should have been gone. I see.